See that we have two boards on here. It's an NI Elvis 2 Plus and the LabVIEW Quanser DC motor. It's a QNet 2.0 version. And so as we can see, it's a pre-assembled board, so all we need to do is just like attach them to each other because it has connections for it. And so after that we plug in all the cables and press the on button. We don't need to touch anything here because we're going to be using LabVIEW to control to automatically control the board and its behavior. So everything is pretty straightforward, so we can proceed to LabVIEW and the experiment itself. So here it's asking for qualitative PI speed control, but what we need to do is y'all can quickly look through the background and theory, but I'm gonna scroll down to in lab exercise, and this is an example like of how it's gonna look whenever you start the device, and I'll show you that a little bit later. So here it's asking for us to ensure the QNet VI file is open, which I have open here. The way you could find it, I'm not sure if you need it, but like the way you can find it is I think it was provided with let me see. Yes, these files are available online, so you can download them. It's the only 3 files that we'll need for the rest of the experiments, starting lab 7 and finishing with lab 10. For this current experiment, we need to use DC motor speed control, as it's asking for. And the second one, yeah, is asking to run the VI. So I have the VI open right here, and first thing that we need to do is make sure the device is shown in the list of devices right here where it says Elvis device, and then everything else is pretty much set up. So I just need to click the run button, and this is what it does. But I already had the parameters changed, so as this is not what we're gonna see for this experiment. Let me just go back real quick to see what parameters we need. We need 25 for amplitude, frequency 0.4, offset 100, signal square, so that's already there. KP, we need 0.05, and then 1 for KI, and BSP 0. Now we have those parameters. Examine the behavior of the measured speed shown in red with respect to the reference speed shown in blue in the speed radians per second scope. Explain what is happening. So I can quickly explain after I run the file what's going to happen, and then for the rest of this I think students are going to be able to figure it out on their own, because it's pretty straightforward. So as y'all can see, this is an amplitude of the speed in radians per second, and what it does is like every time it follows the pattern of the motor, the way it moves and its behavior. So we can see that it goes slow and then fast again. So whenever it's slow, it's down here, and this is just a movement pattern, or like behavior pattern of the way it moves. Like it's the spikes right here, and whenever it increases the speed, it goes up right here and changes the spikes basically. And so the next thing, let me just pause it for a second, and then there's the better graph to explain everything. It's in lab 8, so we have standard second order step response. So here we have the time. So we have percent overshoot right here. We have the amplitude as a YT, and reference graph is called an RT. So the reference waveform, we just needed to make sure that it's following the right pattern. The actual amplitude that we need is following the right pattern. And so here we have a peak time, which can be calculated using T max and T naught. And what else is here? So this is just to explain the 7's experiment, just because it's a good graph. Here, when we come back, the next step is step 6, when it's asking for incrementing and decrementing Kp by steps of 0.005. So we can, yeah, let me just do that, because I mean, obviously we have the board, so Kp by 0.05. So first I'm going to decrement it, and then I'm going to increment it from 0.05. So this is 45. It's not going to be a drastic change. All I'm just going to do, and another thing is in the voltage graph you can see the amplitude on its own without the reference, so that way you can easier spot the difference. So this is by 0.005. Now let's go down by 1. I mean by 5. Not that much difference either. So in order for us to notice the difference, let's just go down by 2, just in case. I mean down to 0.02. That way we can